Let's start talking about forces on submerged surfaces, really adding the mechanics component to fluid mechanics. Now, as we talk about forces on submerged surfaces for this class, we are only going to look at planar surfaces. If you want to do circular surfaces, there's a couple different things, but I'm sure that you could probably see how this expands out to there. But we're just going to focus purely on a planar surface. So now, as we're dealing with this, we have to remember, as we can see in these two pictures, that pressure is a distributed load. Much like in our mechanics classes, when we've dealt with loads on beams, these are distributed loads. And so we're going to need to figure out three things to be able to use them to solve mechanics equations. And with the distributed load, we need those three things are going to be, we need to know what the concentrated load is. So we're going to need the magnitude of the concentrated load. Now, aside from the magnitude, we're also going to need to know the direction, because it is a vector. And then the last thing that we need to know is the sense. We need to know which way that it is pointing. So out of all these, the sense is going to be the easiest one, because as we stated, pressure is always going to act 90 degrees to the surface. So that kind of takes a part of direction too, because since it's acting 90 degrees to the surface, we know it's pushing into the surface, that's fine. So for the direction, a lot of it's really going to be where we end up having to place that concentrated load. And then we're going to have to do the magnitude of the load, and we're going to do the magnitude in a very similar way that we've done in previous classes when we've dealt with distributed loads. Excuse me. So we're going to look at the horizontal surface first, and we're going to expand everything out. So we're going to be looking for a resultant force, which you're going to call F sub R. And so what is a resultant force? Well, the resultant force is if we take that distributed load, which is our pressure, and then we integrate it over our area, that entire term is going to give us what the resultant force, or what the sum of all the pressures is. Now, for us, this is actually not that hard to do, because what we're going to do is we're going to figure out what the pressure is. Now, for a horizontal plate, in this situation A here, well, it's pretty easy because I know what the force is at every point. The force is not going to vary at all. And so all we're going to do is we're going to calculate out what the hydrostatic pressure is on that bottom plate. And so what is that hydrostatic pressure going to be? Well, it's going to be the pressure of the atmosphere pushing down on top of the water or the fluid, plus the hydrostatic force from that column of fluid. We're going to take all of that and multiply that by our area. And that's all we're going to do for the resultant force on the horizontal plate. Pressure atmosphere plus gamma H times the area. Now, in the case that we have here, as you can see, our tank's sitting outside in the air. And so I have a pressure pushing on the other side of this plate here. Well, that's also atmospheric pressure because that's open to the atmosphere. So if I have atmospheric pressure on the other side of the plate, what happens? Well, that's going to be minus atmospheric pressure, and it's going to cancel everything out. So my resultant force is just going to be gamma H times A. And so it really depends on whether or not you have atmospheric pressure pushing back on the other side. Now, this works for any shape of plate. It really doesn't matter if it's circular, if it's bunched all together and whatnot. It doesn't matter. It can be an oddball shape. As long as you know the area and it's horizontally flat, we can solve things out. So where is that force going to be located? Well, just like when we were doing our mechanics and we were solving for loads on a prismatic beam, I have a regular box loading. What this is, it's going to be right in the middle. And so that's how we take care of a horizontal force. Horizontal forces are boring. Let's look at something a little more interesting. Let's look over here on the side, picture B, and we're going to look at the vertical force on those walls. Now this is more interesting because, as you can see, as we go down in the depth, our pressure increases. And that's because of the hydrostatic equation. But we also know that it increases linearly because the hydrostatic equation, if you recall, is dP dz, how the pressure changes with depth, is negative gamma. So it's a linear equation. So this method of, okay, we still have to take our resultant force, we have to integrate it over the area, and what we're integrating is the pressure. So the thing is, as you do an integral like this, you're basically working out what the average pressure is across that and multiplying it by the area. So the nice thing about this, and because it is a linear equation, if you go right to the depth where your center of gravity is, so HCG, and that's your depth there. Well, if you look at, just graphically looking at it, there's that little triangle there. Well, if I cut this here, this triangle can kind of flip in there and give me now a box load. And this only works because it's linear. If it was a power equation, this wouldn't work out so well, but in this case it does. And because of that fact, it makes it really kind of simple to do this resultant force, because now, if I know that at the height of center of gravity is going to turn this into a box load, what I can do is sit there and go, okay, well, I'm going to take this other equation, just go the force resultant. If I integrate the pressure over the area, it's just going to be the atmospheric pressure on top plus gamma H. Now I just HCG times the area. And this works for the situation where it's a flat plate on the bottom too, because HCG is just going to be the H. And so now, same thing, like in this situation we've got now, I have pressure atmosphere, oops, that doesn't really matter there. I have the pressure of atmosphere pushing on the outside here. And so what I can do is I can also say that all the force resultant is going to be atmospheric pressure will end up canceling out gamma HCG times A. So this is really the equation that you need because it works with both the horizontal plate and the vertical plate. We'll talk about inclined plates in a minute. So that gives us the magnitude. Now where do we apply that force? Let's move on to the next one here. So once again, I've got a triangular load. And so what did we do in mechanics? Well, when we had a triangular load, we needed to put our resultant force at the location of the centroid of the area of the triangle. And so for us, this case, it's pretty easy. It's just a third of the way from the larger end. And so basically that means that all of this pressure here is going to be equal to all the pressure that's coming down up here. And so we can say, okay, well, that's pretty easy, as we just go that, okay, we apply that force at h divided by 3, where h is the depth all the way to the bottom. Now, stuff like this will be important because you'll be solving mechanics equations, and you're going to have to do moments about certain points. And so you're going to need to know exactly where the force is. So what I've given you is the integration method for solving what the pressure is. Now, especially on those vertical walls, we used this whole idea of the pressure prisms to figure out where it goes, and mostly just because it's a lot faster to do that when we have vertical walls. Now, the real issue comes, what happens when I have, when I have a computer that is not really jiving with me, what happens if I have a plate underwater that's at an angle? That little triangle symbol with the 3 lines just means that denotes it as a free surface. So I have atmospheric pressure, I have some plate under the fluid. Well, how do I figure out what the magnitude of the pressure is? Or so what is my resultant force and where is it located? Resultant force is actually still the same. I'm going to draw that's my little symbol for my center of gravity. So my resultant force is going to be the integration over the area of the pressure. And because it's linear, it's going to be the same thing. We're going to just go, well, pressure atmosphere plus, we're going to add to that the height of the center of gravity times gamma times the area will give me the resultant force. One thing to note in this case that we're showing right here is there is no atmospheric pressure on the other side, so that's the pressure that we're going to have. pushing down on the top, pushing down on the plate because I have the plate submerged in water. If I had cut this off and made it exposed to atmosphere on the other side, then we would take the atmospheric pressure out. So now, the interesting thing becomes, well, where do we put that force? Well, we're going to have to calculate out where it goes. And so we're going to have some angle here. This plate is some angle in the depth. Now, there are two different, it's the same equation, but they have different notation between your book and the Nice Engineering Equation Manual. As if you can look at the equations, basically in your book is going to calculate out the distance from where the center of gravity of the plate is to where you're applying the force. In the engineering manual, it's just going to calculate, it's going to put all that in one thing and go all the way down from the surface to where the force is applied. I'm going to give you the notation out of the engineering manual and talk about it in that context, since that's what you're going to be using for your exams. So where this is applied, all these forces are going to be applied at what's called the center of pressure. So the center of pressure is where we apply all of our resultant forces. Even in the other ones, it's still called the center of pressure. And so that is going to be our direction. Now, the way that the engineering manual calculates things out is instead of using H's, what we're going to do is we're going to do Y. Now, Y is the distance along the plate at whatever angle it is, and that's going to be called Y sub C. And so you'll be able to calculate that out using regular trigonometry and whatnot. The distance to the center of pressure is going to be given by YCP. Now, this could be a little bit confusing because in your book, when they talk about YCP, they're talking about the distance between the center of gravity and the center of pressure. So you just need to pay attention to where you're pulling your equation from. Now, at this point, it's just a simple equation. I'm not gonna have you derive it or anything. And it's basically that YCP is going to be equal to YC, so that's the distance from here from your surface to the center of pressure, plus gamma sine theta, the moment of inertia about x, about the centroid. Your book will call this IXX, divided by the pressure at C, which is the pressure at the center of gravity, times A. And so that's the equation that we're going to use. I'm at the end of what I can record for this video, so the next video, we're going to talk a little bit more about that equation.